Hello everyone. In this video we will talk about power series and specifically how they can be used to represent certain common functions that we know. So first let's just recall the definition of a power series. So it's a series of this form, and the AK here is what we call the coefficient, and the x naught here is what we call the base point or the center. We would say like our power series is centered at our base point x naught. Most of the time we like to have x naught be 0, but not always. So I'll just say usually here. So a nice example was just take all of the monomials of the form x to the k, add them up, and we said that this, because it's a geometric series, right, where r is x and a is 1, right, this is 1 plus x squared plus x cubed and so on. Well, we know geometric series, it would converge to a over 1 minus r, or 1 over 1 minus x, but only if the absolute value of r is less than 1, and so this would be for all x in the interval from -1 to 1. So basically, this is a way to represent this function with an infinite polynomial, but it's only accurate on this interval. Now let's talk a little bit more about the interval or radius of convergence. So on the last one, the interval of convergence was -1 to 1. In general, it's more common to find what we usually will represent by capital R, the radius of convergence. And it turns out that all power series will converge on a symmetric interval around your base point. So if r is the radius of convergence, then the interval of convergence is x naught minus r to x naught plus r. So in the last one, right, we were centered at 0 and we had a radius of 1, and so we went from -1 to 1. So let's actually see this with a little bit more practice, and we'll see that we also need to be a little bit careful about the endpoints. So I'll just put some question marks there for now. All right, so this is a complicated looking thing. So we have our coefficient here, right? And then this one is centered at 5. And we want to know, when is this going to converge? So this isn't geometric, but we can always look at these and ask, how do they behave long term, and are they like a geometric series? So what we will always use is the ratio test, and specifically we will do it for absolute convergence. So what I'm really saying is, look at the k plus 1th term, which here, right, like our coefficient was ak, so the coefficient, but the k plus 1th coefficient, and then your x minus x naught to the k plus 1th power over the same thing for the kth term, but take the absolute value of this, because of course x could be negative, or x minus x naught, I guess more specifically, could be negative, so you want to worry about whether the ratio test would apply. So we slap some absolute values on it, and we make sure that everything is positive. So this tells us how to find our radius, right? So if this is less than 1, then we know it converges, right? And if it's greater than 1, it diverges. The issue, of course, is when it's equal to 1, we don't know. So the less than 1, this is going to help us get our radius. And then to get the actual interval, whether to include the endpoints or not, all comes down to what happens when it's equal to 1. So this is where we get information about the endpoints. Okay, so I've already gone ahead and put the first step of the ratio test here, and I have multiplied by the reciprocal because I don't want to have humongous fractions stacked on each other. So we can get a lot of cancellation here, right? So remember that absolute values pass in and out of, multiplication works over the absolute value, same with division. So we can go ahead and cancel all but one of these 4s. We can cancel all but one of these x minus 5s. And we can cancel all but one of these -1s, but really those don't matter at all anyway, because we're taking the absolute value, and that's just telling us what sign it is. And we know it's going to be positive. So we can rewrite this now as k times x minus 5 over 4 times k plus 1, all the absolute values here. I just distributed it over addition. And this is where I'm fine with you just saying, hey, these are the same power. The plus 1 doesn't matter in the long term. So this is going to go to the absolute value of x minus 5 over 4. And I took the absolute value away because 4 is positive. And so this will converge. And I'm just going to call this s of x so I don't have to write the whole series every time. So I just named it s of x up here. I'll use it down here as well. So this series converges if this ratio is less than 1, right? And it would converge absolutely in that case because I took the absolute values there. Well, now you just want to solve for that. So we multiply over by 4. And so this guy is our radius, right? We're centered at 5, and this is telling us we can go 4 in either direction. So this is r. This is our radius. So basically, we know it converges for x between 1 and 9, right? 4 on either side of 5. The question is, what happens at 1? What happens at 9? So s of 1, right, you plug in the left endpoint 1. You can literally plug it in. It's 1 minus 5, or negative 4 up here. And, well, negative 4 to the k, negative 1 to the k, well, those are the same sign. So this is just 4 to the k, okay? So our cancellation here is almost everything. You basically boil this down to the sum from k equals 1 to infinity of 1 over k. That's the harmonic series. So it diverges at the left endpoint. And then at the right endpoint, we would get positive 4 to the k up here. So again, we get cancellation. But we still have the negative 1 to the k this time. So it's alternating. This guy would converge, right, conditionally by the alternating series test. And so what do we know then? Our interval of convergence. So we found the radius was 4. The last thing was to worry about what happens at the endpoints. And we get that it converges not at 1, but it does at 9. So it's a half open interval. So for your first exercise, I want you to find the interval of convergence for x to the k over k factorial. Or I guess I'm going to tell you what it is already. It's negative infinity to infinity, but I want you to show why. Okay? So I want you to justify this using the ratio test. And the reason I told you is this is actually going to be the next thing we look at. Okay, so let's look at this a little bit more in depth. So my claim is that 1 plus x squared over 2 factorial and so on is actually e to the x. So the claim was also that this is true on negative infinity to infinity, right? So this is actually saying that these are the same function, that I can express e to the x, this exponential with this irrational base, as an infinite polynomial. And we'll find later that it's a pretty good approximation even with a finite degree polynomial where you don't have to take the whole series. You could cut it off at a certain point. And this can be really useful for looking at certain things because, plugging numbers into x or x squared that are integers, for instance, is much easier than thinking okay, e to the 7th power. That's a lot harder for me to hold on to than 1 plus 7 plus 49 over 2, plus, those are a little bit easier to see. So why is this e to the x? Well, what defines e to the x? It's kind of two things. One, it's that s prime is equal to s, right? The derivative of e to the x is itself. And the other one, because that's true for kind of a family of functions, it's also that at 0 it is 1. Okay, so one of these is very easy to check. S of 0 is plug in 0 for all of these x's here. And, well, we're only left with this first coefficient, right? So this is true. Now, why is s prime equal to s? Well, look at these derivatives. So I'll put them in blue under here. So this is 0, so I've kind of shifted things, but then I get 1. 2x over 2 factorial, which is 2. That's x. I get 3x squared over 3 factorial. My 3's cancel, and I'm left with exactly x squared up top and a 2 factorial down below. The next one would be x to the 4th, and I would get 4x cubed over 4 factorial. The 4's would cancel. This becomes 3 factorial. And so you can see that you get exactly the same thing back. And so this indeed is a different way and sometimes a more convenient way to view e to the x. So this also works for some trig functions as well. So sine of x actually can be represented as this infinite series, which looks like kind of all of the odd terms in e to the x, but alternating signs. And this is also true for all x. So this would converge everywhere. And so for your next exercise, I want you to find a power series representing cosine of x. So think about, you know sine. How do we get from sine to cosine? What is something we could do to all of these terms to get to another infinite series giving us cosine? So that's my hint there. So let's look at one more way we can do this. So now this one was only true on -1 to 1, but we saw that 1 over 1 minus x was this series. Now you could get a little bit clever here and say 1 over 1 plus x then. Well, I can put it in this form, right? It's 1 over 1 minus negative x. So this is like my r, and my a is up here as 1. And so this is also a geometric series. So this should start, k equals 0 to infinity, a is 1, and my r here is negative x instead. So basically, note what I did, right? I have x here, I switched x with negative x, and I just get negative x in here. And if you wanted to write this with like the coefficient separated, you could do -1 to the k, x to the k. And so your last thing I want you to do here, I want you to write 1 over 1 plus x squared instead of 1 over 1 plus x as a power series. And this will be a little legwork that we'll take advantage of next time. Thank you for watching.